All right, so we're starting section 4.3, which is on undamped forcing and resonance. Now, with undamped harmonic oscillators, we're saying there are no damping forces. So there's no friction and there's no air resistance. And that may seem unrealistic because it's not like there's a little switch in the wall where you can just go over and say, turn off friction. It doesn't work that way, okay? But there are scenarios where the damping forces are pretty small, okay? And when that's the case, a model in which there's no damping force can be a reasonable model. Remember, we always make simplifying assumptions when we're trying to use a differential equation to model a real-world situation. And so sometimes going from a very, very small damping force to, it's negligible, let's neglect it, is a reasonable assumption to get something that sort of mimics what actually is going on. So that's the application of this, that this would be when the damping forces is small enough to be negligible in the context. Okay, so I've got here an equation corresponding to an undamped harmonic oscillator because there's no y prime term, so the damping coefficient is 0. And then we've got a forcing function, which is cosine of omega t. That's an omega. It's a Greek letter. It kind of looks like a W, but it's actually an omega. What I'm doing is I'm not yet specifying what that is because I want to take a look at what we get for different angular frequencies. So a little bit of vocabulary rule here. If I have cosine of omega t or sine of omega t, omega is called the angular frequency. Of that function. Okay. Now the period of that function is 2 pi divided by omega. So the period would be the amount of time it takes for this function to go through one cycle. If omega were 2, the period would be pi. Because if we're taking cosine of 2t, we're going twice as fast as usual, and so we're going to get a full cycle over an interval of length pi rather than the usual period of 2 pi. And then the frequency is just the reciprocal of the period, omega over 2 pi. Now, that's different from the angular frequency. The frequency is just the number of cycles that would be done in one period of time. So if the frequency is 5, then 5 cycles happen every second. So frequency is the number of cycles that we have. And since we associate a cycle with going around the unit circle once, which is rotating through 2 pi radians, notice that the angular frequency is just this times 2 pi. So basically the angular frequency is, instead of saying this many cycles per minute, this many radians per minute or second or whatever unit of time. Okay. All right, so we're going to be taking a look at all of these things, and for right now, I want to solve this with an unspecified angular frequency for my forcing function. Okay. So, I know that my general solution is going to be a solution to the associated homogeneous plus a particular solution. So the associated homogeneous equation is y double prime plus 16y equals 0. Characteristic equation is s squared plus 16 equals 0. Okay. And that's going to mean s is plus or minus 4i. Now I can certainly use the quadratic formula to get that if I want to, but notice that's just s squared equals negative 16. So s is going to be plus or minus the square root of negative 16, which is 4i. Okay. So when we have that, we will get that a complex solution. Now I haven't yet complexified the equation. Right now I'm just talking about a complex solution to this same differential equation. I'm going to use y tilde here to mean a complex solution to here. I'm going to recycle that notation later when I complexify. Okay. So y tilde would be e to the 4it, which I know is just cosine of 4t plus I times sine of 4t. So the real part is cosine of 4t, the imaginary part is sine of 4t, and so I know that any solution to the associated homogeneous is just going to be some number of the real part, cosine 4t, plus some other number, we'll say k2, of the imaginary part, sine of 4t. Okay, so we've got that much, k1 cosine of 4t plus k2 sine of 4t, that's my y sub h, and now I need to add to that a particular solution. So, cosine of omega t is the real part of e to the I omega t, so I'm going to complexify. Now I'm going to just recycle some notation here. Here I was using y tilde to mean a specific complex solution to this equation. When I complexify, I'm creating y tilde as an unknown complex function that satisfies the corresponding complex differential equation, e to the I omega t. And I'm just going to make a note that yp will be the real part of yp tilde. So if I can find a particular solution to this complexified equation, its real part will be the particular solution that I was looking for to my real differential equation. All right, so we're going to guess. So we're going to guess a e to the I omega t. That's going to mean, so that's my yp tilde. So then yp tilde prime would be I omega times a e to the I omega t. Chain rule always just gives us a copy of the coefficient in front of t. So yp tilde double prime, we're going to get another I omega. Two i's is an I squared, that's a -1. Omega squared a e to the I omega t. All right. Okay. So if I plug into my complexified equation, I'm getting negative omega squared a e to the I omega t plus 16 copies. Oh, I don't even need, right? There was no yp tilde prime. Good grief. Because this was undamped. So just plus 16 copies of a e to the I omega t. And I want that to equal 1 copy of e to the I omega t. Well, if I take a look here, I can factor out the a times e to the I omega t. So I've got a e to the I omega t is being multiplied. I'm going to actually keep that on the right. A e to the I omega t is being multiplied by 16 minus omega squared. Now, if this is going to work, the coefficient in front of e to the I omega t has to equal this coefficient, which of course is just 1. So I've got 16 minus omega squared times a has to equal 1. A is going to equal 16 minus omega, A is going to equal the reciprocal of 16 minus omega squared. All right, notice what's on the bottom here is the angular frequency that I have for the natural response, squared, minus the angular frequency that I have for the forced response, squared. Because we're going to end up getting now sines and cosines of omega t. All right. So we have yp tilde is 1 over 16 minus omega squared e to the I omega t, which is 1 over 16 minus omega squared times cosine omega t plus I times sine omega t. And so there's my function. I wanted the real part, so my y sub p is yp tilde, the real part, which is just 1 over 16 minus omega squared times cosine of omega t. That's my particular solution to the real function. All right, and we can pretty much generalize this. If I had a different number here, I could just go through and basically I'm going to get that number, which is the angular frequency of the natural response squared, minus omega squared, the reciprocal of that, times e to the I omega t, and then the real part will give me cosines, and if I had a situation where I wanted the imaginary part, it would be the sines. So this is going to generalize anytime I have a situation where I've got an undamped harmonic oscillator and the forcing function is just sine or cosine of omega t. I will get 1 over this number, which is the angular frequency of the natural response squared, minus omega squared, times, if it's real, cosine of omega t, if I want the imaginary part, sine of omega t. Okay, so what I want to do now is take a look. This, by the way, of course, supposes that omega is not 4 or negative 4, so that I'm not getting 0 in the bottom. But what I want to do is take a look at what we're getting if omega is close to 4. I want to take a look at how the angular frequency of the natural response and the forced response interacts to affect my overall solution. Notice, because this is undamped, my solutions to the associated homogeneous equation are not going to 0. So this is not a steady state solution in this particular case, or in any case where I have an undamped forced harmonic oscillator. So I want to take a look at how this trig function interacts with that trig function. Okay, so that's where we'll pick up next time.